In the previous video, we introduced band diagrams and you learned about the conduction and valence energy bands. Now, we will take a deeper look at the charge carriers that can occupy energy states within those bands. The occupation of energy states in the valence and conduction bands of semiconductors determines the concentration of charge carriers. The concentration of charge carriers is a very important property for understanding the performance of solar cells. Let's start with the equilibrium condition. We define equilibrium of a system as a state in which the system is unperturbed. Therefore, no external forces are applied to this system. These forces could be external voltage, magnetic field, illumination, or mechanical stress. We can define thermal equilibrium in a system as the condition in which its parameters do not change over time. We use the word thermal because the equilibrium conditions will change depending on the temperature. Several steps are taken to determine the concentration of carriers in a semiconductor. The first one is to determine the available energy states for electrons in the conduction and the valence bands. In the previous videos, we have described the concept of energy levels and energy bands. We saw that only a few of the levels are effectively occupied by charge carriers. On the left, you can see our familiar simplified band diagram, with the conduction band in yellow, the valence band in blue, and the band gap in white. The density of energy states, which we denote by G, is an important parameter telling us the number of allowed energy states per unit volume as a function of energy. Here, you can see how the density of states varies with the energy. We have the density of states on the x-axis and the energy level on the y-axis. You can see that there are no allowed states in the band gap. Then, the further we move from the edges of the bands, the more energy states are available. Gc represents the density of states in the conduction band. If you remember from the previous video, the conduction band represents energy states of mobile electrons. Gv, on the other hand, represents the density of states of holes in the valence band. Holes essentially occupy the states in the valence band of missing electrons, that is, the electrons that have been excited to the conduction band. You will learn much more about holes in the future videos. For now, let's look into the equations that represent these densities. Here, you see our density of states function plotted again. Let's look at the conduction band. We can express the equation for the density of states in the conduction band as follows. I will not derive this equation, but you can learn more about it in the textbooks. The equation is based on a few constants like the Planck constant h and the effective transport mass of an electron mn star. The dependence on energy is a square root relationship. As the energy gets further away from the conduction band edge, denoted by EC, the number of allowed energy states increases. Now let's continue with the valence band. The equation of density of states in the valence band is very similar to that of Gc. But now we have to use the effective transport mass of holes, MP star, instead of that of electrons. In most common semiconductors like silicon and gallium arsenide, the effective transport mass of a hole is larger than that of an electron. This difference makes the two curves asymmetric, resulting in the valence band density of state being larger than that of the conduction band, especially away from the band gap. So now we know the density of allowed energy states of mobile electrons and holes. To calculate the total charge carrier concentrations, we also need to know how many energy states are really occupied. For this purpose, we introduced the so-called occupation function, also known as the Fermi-Dirac distribution. The Fermi-Dirac distribution function expresses the probability that an available energy states will be occupied at a certain temperature. This function depends on the difference between the energy level of interest E and the so-called Fermi level EF. I will explain the definition of the Fermi level in a couple of slides, but let's first look at how this distribution function depends on temperature. At 0 Kelvin, the Fermi-Dirac distribution function is a step function. It means that only the energy levels below the Fermi level are occupied. Energy states of the conduction band which are above the Fermi level are empty. So no electrons occupy those states. However, if the temperature goes up, the probability of occupation of a higher energy levels increases. The more temperature rises, the probability of occupation gets higher, and more electrons can fill these states. This is the result of thermal excitation. The excited electrons are getting energy from the ambient heat. If the temperature is above 0 Kelvin, electrons can occupy energy levels above the conduction band edge. Before we go any further, let me explain a very important concept, the Fermi level. So what exactly is the Fermi level? In general, it represents the total averaged energy of the valence electrons of a material. This energy considers the electrochemical energy of all the electrons in the conduction and valence bands. From the Fermi-Dirac distribution function, we can easily calculate that the probability that the energy level corresponding to the Fermi level is occupied is 0.5. The position of the Fermi level in an intrinsic semiconductor is close to the middle of the band gap. Mathematically, the Fermi-Dirac distribution equation can be approximated by the Boltzmann equation, when the difference between the energy level and the Fermi level is larger than 3 times the thermal energy. In the diagram below, we see, in fact, that for E minus EF larger than 0.077 electrovolts, the two curves are indistinguishable. Depending on the position of the Fermi level within the band gap, we can therefore simplify the Fermi-Dirac distribution function if the Fermi level is within 3 times kBT from both the conduction band edge and the valence band edge. This corresponds to the dark gray area in the band diagram. This is known as the Boltzmann approximation and applies to non-degenerate semiconductors for which the Fermi level is not too close to one of the band edges. In this video, we discussed the density of states function and the Fermi-Dirac distribution. In the next video, we will use these parameters to determine the charge carrier concentration.